Okay, let's summarize. Whenever we have resistors in series, each resistor that are from the resistors that are in series should be on the same wire, same branch. It does not matter where they are relative to each other as long as they are in the same branch. Now, because of that, if the resistors are different, the voltage across each of the resistors is going to be different. Remember that the voltage is given by Ohm's law, R times I. V is equal to R times I. The overall voltage over resistors that are in series, we can find it by adding the various voltages. Since they are in the same wire, the current going through each of the resistors is going to be the same. So the overall current is the same current that goes through each of the resistors. The overall resistance of the circuit when we place resistors in series is going to be higher than the resistance of each individual resistor. Now, in the case of parallel resistors, each resistor has to be on a different branch, different wire. The voltage is the same for each of the resistors, for each resistor from the resistors that are in parallel. It's the same voltage. They're subject to the same voltage. However, the current is going to be different for resistors that are different. If the resistors are identical, they will have the same current. But for different resistors, we are going to have different currents. The overall current, like the current here, is going to be the sum of the currents going through each of the branches. The overall resistance that we get by combining resistors in parallel is going to be smaller than the resistance of each individual resistor. And we get the overall resistance for resistors in parallel by using the inverse relationship. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 if I have 3 of them and so on. For resistors in series, we just add them up. Okay, a comparison with capacitors. Now, the equation for capacitance for a parallel plate capacitor is given by this, epsilon 0 A over D. If I have an insulator, it's going to be kappa epsilon 0 A over D. The equation for resistors is rho L over A. When you compare these two equations, they are very much the same. So this is the dependence on the material in both cases, and both of them depend on the physical size of either the capacitor or the resistor. Now, for the capacitors, the area is in the numerator. For resistors, the area is on the denominator. For capacitors, the distance separating the plates is in the denominator. The equivalent for resistors, which is the length of the wire, is on the numerator. Because of that, the equations that determine what happens when we combine capacitors and resistors in parallel and in series are opposite to each other for capacitors than for resistors. For example, for capacitors in series, when we combine capacitors in series, we get a smaller capacitance, and we get the overall capacitance by 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 if we have 3 and so on. For resistors, it's the opposite. For resistors in series, we get more resistance, and we get the overall resistance by adding the resistances. So R equivalent is R1 plus R2 plus R3 plus R4. We add all resistors. For capacitors in parallel, the overall capacitance is going to be larger than the capacitance of each of the individual capacitors. We get it by just adding the individual capacitances. So C equivalent is C1 plus C2 plus C3 and da da da. Now for resistors, it's the opposite. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Now, for energy, for capacitors, they store this amount of energy, 1/2 of QV. Resistors dissipate energy, and the amount of energy dissipated is going to be power times time, where power is given by the product between current and voltage, I times V.